Karlsruhe in Germany. And he's well known for his research on inelastic photon scattering. So yeah, he studied in the Université de Paris and did his PhD in the Université de Diderot and a postdoc at the European Synchrotron. And then in 2009, he became the leader of the inelastic photon scattering group at the Max Planck Institute for Solid State Research in Stuttgart. And then since 2016, he's now professor at the Karlsruhe Institute of Technology, and there he's the head of the Institute for Solid State Physics. And yeah, today he's going to give us a presentation on probing the collective excitations in correlated systems using inelastic X-ray scattering. So we're looking forward to your presentation.
Thanks a lot for. Okay. So I put this thing. Can you all hear me, or I have no idea whether it works. It seems to work, but really close. Okay, good. Excellent. So thanks a lot for the kind introduction. That's how you do an introduction. So that's the title I gave last week when I was asked to give title, and I was asked to give title much longer before that. And I put this together, and to be completely honest, I finished to decide exactly what I'm going to talk about like half an hour ago. So I maybe changed a bit my title, to make it a bit more, not complete experimental survey is a bit ambitious, but I would just probably give you the principle of the idea of probing collective excitation in correlated system and give a few recent examples. These are some brief outlines. So why being interesting in collective excitations, or why excitations are exciting, I guess. How to actually measure them, and I will show you that the conventional tool to use that to measure them is usually neutron scattering, and there are many other probes that you can use. But why bothering? I mean, so I will be forced to highlight some of the problems that neutrons have to advertise for X-rays. And just right now, I can tell you there are many other things you can use. You can use electrons. You can use helium atoms, sort of thing. I'm just going to focus on X-rays, and that's already quite a lot. Note that I'm the first seminar speaker here. It's a bit of an unusual format, 1.5 hour. So I will make really more like an overview. Huh? And then, so to finish, I will give, I would just focus on 2 examples. So Charge-density waves in dechalcogenides and magnetic excitations in various transition metal oxides using RIGs. So please feel free to interrupt me anytime. And if you ask your question now, you won't be accused of postponing the aperitif at the end of the session, which I understand is taking place. In that sense, I have the best talk, right? I mean, this is the best slot. Okay, so let me start. Why being interested in collective excitation? So I think generally collective phenomena are fascinating. I mean, I really like the idea of emergence, the idea that, if you look at this wave, you can understand as much in the greatest detail a molecule of water, but it doesn't allow you to understand how waves form based on the collective motion of billions and billions of molecules of water. In the same orders of ideas, when you see this kind of collective motions, you can understand very well or think you understand very well the individual behavior of people, but if you take one of these guys alone, it's just jumping alone, it just looks ridiculous. But apparently, it has more impact when it's done collectively. So it's just a matter of saying that collective excitations are basically the archetype of emergent phenomena, so things that do not make any sense from particle alone. And this is really a good illustration of this idea of Phil Anderson, that more is different. Okay. Of course, as I was preparing this, typically yesterday evening, I Googled, just in case, what do you find on Google if you look at collective excitations? Google collective phenomena? Well, I Googled collective excitation, so I thought maybe I would get something a bit nasty. Actually, I found something very useful. PR paper reveals the role of collective electron excitation in helping cancer treatment. So I have to think putting this in my next grant application. So collective excitations are actually useful for cancer. And well, it looks semi-serious. Apparently, some kind of plasmon in nanoparticles that help destroying some things. Well, It's at least it's a peer, right? So for once, it's not some kind of it's not too much of a junk example. Good. So let's be just a bit more serious, and let's think of a piece of copper. You know, I want to understand the thermodynamics of a piece of copper, and to this I need to understand how that piece of copper is going to exchange energy, essentially with the rest of the universe. So that's a bit ambitious. And you know that, basically starting 100, 150 years ago, people started to really look in the details, try to understand why metals are metals and behave as they do. And you can look at these thermodynamic properties. For instance, you know that metals have a specific heat. They have thermal expansion. So specific heat means that basically it's the amount of energy that you have to give to that piece of metal so that it increases its temperature by 1 degree. So, to try to understand, so the measurements were done, I can't even tell you when, but just to jump on the remark that was done yesterday, yes, we know that, now we know that everything is made out of atoms, so even this piece of copper, so if you look with a tunnel, electron tunnel microscope, you will see actually the atoms individually. These are copper atoms, so there are 63 electrons which are in the different orbitals. And even without knowing that, you know that they were electrons, and you try to explain basically the thermodynamic properties of this piece of metal just by using what you can understand from electrons. So you can calculate the specific heat based on basically the free electrons that you will find in the copper. And you know that after some work, I mean, this is elementary condensed matter physics, right? You find that the specific heat is basically proportional to temperature. And what I showed you just before, or this can be plotted another way, you know that the electronic specific, the specific heat of the material, so in this kind of simple metals here, there's always an additional term. So C over T is not just a constant as you would expect just from the electrons. And the reason for that is that you have extra degrees of freedom in the system. And in particular here, you see lattice excitations, so phonons, but you can also see the contribution to specific heat of magnetic excitation and all kinds of degrees of freedom. What I'm trying to say here is basically that you have to take into account not only the electrons, but all the degrees of freedom from the atoms, from the magnetic moment, from the orbital degrees of freedom, to really understand how a piece of material can exchange energy with the rest of the universe. So here is of course a very simple example. I took here the example with the lattice specific heat, so the phonons. But if you look on Wikipedia, which is the next thing you do after Google, and you look at what are the collective excitation you can think of in condensed matter. I found a bunch of them actually. Some of them I had never heard of, like a configuron or a dision, a dropleton. Okay, there's a bunch of them. And what's interesting in these collective excitations is basically they all reflect some fundamental properties of material. So the notions of broken symmetries, for instance, with the Goldstone's theorems are very central here. And more importantly, the coupling of these excitations, so these collective excitations to the electron, can yield emergent electronic properties. And I think the most famous example for that is that of superconductivity, where you have electrons that couple through lattice vibrations to form a new quantum state of matter that you don't understand if you just think of electrons, individual electrons without interacting. So of course, this is a huge list. I'm not going to go through all these elementary or these collective excitations, and I'm mostly going to focus on two of them, phonons and magnons. I'm going to try to tell you why it's interesting to look at them and what we can learn and how we are measuring them. So to really set the stage here a bit more in detail, I take the example of this material. So this is calcium ruthenate. So it's a perovskite. It's an antiferromagnetic metal. Sorry, insulator. It's an antiferromagnetic insulator. Spoilers. It has this structure here. So you get this magnetic moment of the ruthenium that are alternating here. So in layers. So it's basically a 2D antiferromagnet. And you might wonder what is the minimum model you need to describe the physics of this material. And so usually when you have to deal with an antiferromagnet, you can think of using a Heisenberg model. So you have the energy level here, the orbital degrees of freedom of the ruthenium atoms that are, so the degeneracy of the d level are splitted in the crystal field of the ruthenium oxygen octahedron here. And you use Hund's rule to fill up the energy level, and you basically got a spin 1 magnetic moment here. And you can calculate the Magnon dispersion of that object, okay? And you will find something like this, okay? So this is basically the magnetic susceptibility, or the as function of the momentum here and the energy. And you will find a Magnon spectrum which has that shape. So detail here do not really matter, okay? But ruthenium is a 4D metal, and it has a sizable spin orbit coupling. So this picture here, where the orbital moment is 0 and the spin is 1, it might not be the right one. And you might think of an object which is instead a strong spin orbit coupling, which completely changes this energy level. And instead of thinking in this way, you know, you put the spin orbit coupling here, and you get a spin orbit singlet with magnetic with S equal 1 and L equal 1. In that case, the magnetic excitation spectrum is going to look completely differently, okay? So here, instead of going basically to 0 at the antiferromagnetic wave vector pi pi, I've got a gap, and I get also a fully gapped magnetic excitation spectrum at the gamma point. So these are two completely different way to describe the system, and the only way to discriminate between the two is to actually do the experiment and measure that quantity. And so to do that, usually you do inelastic neutron scattering. So here is the magnetic excitation spectrum that has been measured using inelastic neutron scattering on these single crystals, and you see how the dispersion, so the dispersion is basically how the magnetic excitation energy change as function of the momentum in the crystal. And you see that they look like this. And if you try to compare with the two calculations, so obviously this looks more like this than like this. And actually, you can take now the spin orbit entangled model and really calculate completely the full dispersion here, and you find actually quite a good agreement with the experiment. So that tells you that you can, just by looking at the collective excitation spectrum and trying to understand it, you know, basically from scratch, you can really identify what are the ingredients that you need to describe properly the physics of your system. So this puts really strong constraint on the description of your system. So how do we actually measure excitations? So one way is to do inelastic scattering, and the principle is actually very simple. Okay, so you start with an incident particle, which has usually well-defined energy and momentum, which are the two quantum numbers that you can use to describe a particle in the free space. Okay, and you basically send it onto an interesting system, and it's going to scatter, which means it's going to change its direction, so its momentum and eventually its energy. So if you want inelastic scattering, you need to change the energy. And because of the conservation of energy, the energy that the particle is gaining or losing during the scattering event is going to be transmitted to the system. Okay. So conservation laws are very important, as usual in physics. So basically the energy that's what I just said, so the energy that is transferred from the probe to the system is transferred to the system in terms of excitations. Okay, you cannot, you have to excite the system, so following a precise protocol. So these excitations are quantized, and there's a lot of them, but they are well defined. And there's a momentum transfer. So if you look at how many particles are scattered in a given direction, you're able to probe the dispersion of the excitation, and therefore learn everything about them. So when I was talking about these things a few years ago, I started wondering, but who had the idea of this inelastic scattering? And the oldest example I found of the prediction of inelastic scattering is actually from Brillouin. So Brillouin is French, okay, but it's something I learned only recently. He's French, but he spent the last 20 years of his life in the US, and he ended up, and he was born French and he died American. But he was French, so you see that the first paper on this is Diffusion de la lumière par un corps transparent homogène, was written in the compte rendu of the French Academy of Science in 1914. And at that time, you know, the language in which you would translate your paper so that many people read it was actually German. After 1914, it stopped being fashionable. And so there was a German version. So, and basically that's where he introduced the scattering of light by sound waves, so that are acoustic phonons. So interestingly, so this was the first prediction of inelastic scattering that I found, and this was only observed 50 years later by actually Charles Townes, which is the guy who invented the laser. Yeah, maybe it's time for a little quiz, you know. So here it's about scattering of visible light, okay? So if you think of visible light, what's the energy of visible light in electron volt? Okay. Hmm? What? Electron volt? It's 2, yeah. Okay, 2 eV is right. This is 400 to 700 nanometers, maybe, but or 300 to 600 nanometers. So it's basically 1.5 to 3 eV. So that's 3 to 600 nanometers. And if you think of a normal solid, you know, typical solid, which the interatomic spacing is of the order of 3 angstrom, of course, the wavelength of light is much larger than the interatomic spacing, which means that the electric field of visible light is fairly homogeneous at the scale of the atomic scale in the system. Which means, we are going to see that later, that the total momentum transfer that that visible light can provide to the system is really small. It's close to 0. So there's a lot of cool things you can do with visible light, and I've seen some posters here of people doing terahertz absorption and things like that. You can do Raman scattering, you can do Brillouin scattering, but all of this is at Q equals 0. And because I'm going to talk today about dispersion, I'm not going to focus anymore on visible light. But I still wanted to mention this because this was the first prediction of inelastic scattering. The first observation of inelastic scattering, interestingly enough, was with X-rays. It was a few years later. It's the Compton effect. So it's in a completely different context. I'm not sure whether Compton ever read that paper of Brillouin. I'm not sure how good was his German. And basically, the Compton effect is the inelastic scattering of X-ray from free electron in atoms. So here you see a spectrum that you can find actually on the Nobel lecture on Compton. And if you never did that, I strongly recommend you to go and to visit, you know, the Nobel Prize websites, because for each of these Nobel Prize you have a very nice lecture, which is usually very pedagogic about the research that the people did and how they gained the Nobel Prize. And basically, so this is here using X-ray. So this is a X-ray line from molybdenum alpha line. And you can see that this is basically your incident light. So you get some kind of monochromatized light. And if you look at the scattered light here, you see 2 peaks. Okay, 2 peaks at 2 different Qs. In that language means that you essentially have now a distribution of energies in your beam. So the difficulty here is that these X-rays have an energy of 17 kilo electron volt, or a very short wavelength, so that's good for our purpose. But the energy difference here, I have not calculated it, but it's basically a fraction of kilo electron volt. So that's a very, very large energy compared to the energies that are usually at play in condensed matter system. So we're going to go back to that in a minute. Nevertheless, Compton scattering once in a while is still used. For instance, here in this recent paper, or not so recent, imaging doped hole in cuprate superconductors with high resolution Compton scattering. But I have to say in most cases, so Compton scattering is prominent when you have very, very high energy photons and you don't know what to do with them. So Compton scattering is important also for nuclear physics and things like that, but for condensed matter, not so much used. So just to get back a bit what we want to measure, so we want to couple our probe to interesting excitations. And the goal is to really get a decent cross-section and a measurable signal. We want to be able to resolve the excitations, which means that we want to be able to sufficiently discriminate the energy of the scattered particle, going to get that in a second, and we want to study their dispersion, meaning transfer momentum to the system. So again, the relevant momentum is typically the size of a Brillouin zone, so it's of the order of inverse angstroms. And the relevant energy, that's a different story. So probing the dispersion of the excitations, meaning looking at the energy of the excitations as function of momentum, okay, and then you can find a model that describes this well. And the energy you're talking about is very dependent on the type of excitation that you're looking at. So if you think of phonons, typically these are energy of the order of 0 to 100 milli-electron volt, depending on the system. So there are systems where you get phonons that goes to higher energies. For instance, in diamond, which is a very high sound velocity, it's very stiff material, so you get phonons up to 200 milli-electron volt. But in most of the materials, usually you get vibration up to 80 milli-electron volt or something like that. Magnons, or magnetic excitations, they can go, they can vary a lot, from micro-electron volt to hundreds of milli-electron volt, depending on the strength of the magnetic excitation. And that's actually one way to measure the strength of the magnetic coupling in a magnetic system, is to actually measure the dispersion of the magnons. And then you get other kind of excitations. You get, for instance, DD excitations, which have electron volt, plasmons, which have tenths of electron volts, so things like that. So there's a whole variety of things. So typically, you want to get a range of, energy resolution between micro electron volt and electron volt. And of course, you cannot do that with a single apparatus. So to be able to nicely see the dispersion, you need to be able to have a good momentum resolution and a good energy resolution to discriminate these things. And again, what is a good energy resolution strongly depends on the kind of excitations you're interested in. So the requirement, it doesn't make sense to have a micro electron volt energy resolution if you're looking at plasmons. On the other hand, if you're looking at phonons and you come with a 1 electron volt energy resolution, that's also not going to help. So what we can easily scatter usually are photons. So I call this quantums, particles. Photons, neutrons, or electrons. These are the mostly used thing in condensed matter physics. So they all have slightly different descriptions. So of course the photon is described by an electric field. So it has a polarization. It's a wave, and if you try to look at the energy of a photon at a wavelength of 1 angstrom, which is typically the order of magnitude of the particle energy or the particle wavelength that you need to cover the full Brillouin zone, you get to 12.4 kilo electron volts. So these are X-rays. So this is the electromagnetic spectrum. So 2 electron volts is pretty much visible light. And nice, I found one without energies. So that was really done an hour ago. So anyway, so the wavelengths here. So the relation between the wavelengths and the energy. So for 1 angstrom of wavelengths, you get an energy of 12.4 kilo electron volt. Sorry, I'm back. For neutrons, it's a bit different. So a neutron which has a wavelength of 1 angstrom has an energy of 80 milli-electron volt. So you can see here already that if you want to measure, for instance, phonons or magnons, which have an energy of the order of 0 to 100 milli-electron volt, well, neutrons are going to be nice. And you can also do this with electrons, which are somewhat energies intermediate. So I'm not going to talk about electrons, although there are really cool things that are done recently with electrons. So after the observation of the Compton effect, so there was the first, just before the observation, there was actually a theoretical prediction of inelastic scattering of light by a Smeckel, by any kind of excitation, so not now acoustic waves. And the first quantum description was given by Kramers and Heisenberg. And again, that's a German paper, but if you know a bit of German, it's actually very nice to read. That's where I realized that German was actually very nice to do science. Too bad they screwed up. So basically what they did here is to calculate the transition rate corresponding to the excitation or the inelastic scattering of light through an atom. Well, we're going to do that in a second, and usually the way to do it is to calculate, transition probability using the Fermi-Golden rule. But what is nice in that paper is that actually it was written before the Fermi-Golden rule was done. So you see, this is really that's good stuff. So when we do the experiment, what do we do? So we start with a fairly monochromatic flux of incident particle. Okay, so that's our flux here, and we look at the scattered particles in a given direction. But when you do the experiment, usually you use a detector, and that detector, however hard you try, has a finite size. It has a finite size and a finite energy resolution. So, which means that you're not going to look precisely in one direction. You're going to look in a solid angle, okay, which is defined by the size, by the area of the detector and the distance to the sample. And you want to know how many particles you're going to scatter within that solid angle, which have an energy which is between, so so omega s here and omega s plus delta omega, so an energy range defined within delta omega. So this could be your energy resolution, for instance. Okay, and this number of particles is defined like this. So it's basically proportional to the incident flux, it's proportional to the solid angle, and it's proportional to the energy width, and to a quantity here that has the dimension of the derivative against a solid angle and an energy of a surface, which is the double differential scattering cross-section. So now let's just start the part which is a bit more formal in that seminar. But basically, to calculate this, you need to calculate transition probability of the system from an initial state to a final state under a certain perturbation. And to do that, you used time-dependent perturbation theory and the Fermi-Golden rule. So that's basically the result. So what you have here is basically the density of final state for the particles. So how many states are allowed in my final state. You get a delta function for the energy conservation. So again, the incident energy, the scattered particle energy, and the transferred energy have to be to fulfill the energy conservation. And you get some average on the initial state of the sample, some kind of thermodynamic average, if you want. So the really annoying part of that calculation is this matrix element. Okay. So again, this is coming from perturbation theory. So here I put this in the first order of the perturbation. In the second order, the states that are involved here are the states of both the sample and the particle. So sorry. Okay. And we have to calculate this matrix element for a given perturbation Hamiltonian. So, and this perturbation Hamiltonian is the effect of the probe, so of the particle on the sample. So it's going to really depend on the problem and on what you look at. So if you want to know, for instance, the cross-section of neutrons when you look at phonons, well, you have to take the relevant interaction parameter, which is that neutrons basically have no charge, so they don't interact with the electrons directly. They will interact with the nucleus. Okay, so you take the Hamiltonian for interaction of your neutron with the nucleus, which looks like this. Okay, and that's basically a sum over all the nuclei in the system of a sum of delta functions, which is weighted by this parameter here, B, which is basically known as the scattering length. So this is not something that can be calculated. This is something which is determined by the experiment. It varies for the different isotopes of your nuclei, and this is basically tabulated. So depending on the kind of nuclei that you look at, you can have sometimes a negative scattering length. So for instance, between hydrogen and deuterium, you get a big contrast. And so different isotopes have very different scattering lengths. And okay, this is basically a formula here. And if you look, for instance, at magnetic scattering, now you take into account the fact that your neutron has a magnetic moment, and that magnetic moment is going to couple with the magnetic field which is generated by the electrons, okay, and the electronic cloud. So just going to look at phonons for a moment here. So if you do the full calculation, you find something that looks like this. So there's a Bose factor here that essentially, so this is just for Stokes process. So that's when I create a phonon in the system. So basically, this Bose factor is telling me that I'm going to have more scattering if I have higher temperature, because then I will have more thermally excited phonons in the system. And you have the scattering length, you get a dot product of the transferred momentum and the phonon's eigen displacement. I'm going to that in a second, and a delta function for the phonon frequencies. So that looks a bit obscure like that, and the worst of all, it looks like the scattering cross section is basically a sum of delta functions at the energy of your phonons. So of course, if you do an experiment, that's not what happens. That's a real spectrum that you get from neutron scattering. Okay, so you place yourself at a given momentum, so given angle, and you see some peaks. Okay, and none of these peaks are actually delta functions, so they all have a finite width, because that's an experiment. So you will first have your instrument has a finite experimental resolution, and the second thing is that the phonon themselves are no delta function. They have a finite lifetime, which depends on their coupling with the rest of the electrons, so the other phonons, and contains a lot of interesting physics, okay, that you want to determine. So that's for phonon scattering with neutrons, and then you get the cross-section for magnetic scattering. Okay, so then it has different factors here. The important thing is that it basically is directly, you can show it's directly proportional, or it's directly probing the magnetic susceptibility of your system. There is an orientation factor which tells you that you can only probe the magnetic moments which are perpendicular to the transferred momentum in the system. So this is mostly geometry, how to align your sample and how to do your experiment. And there is a magnetic form factor which depends on Q, and that comes from the fact that basically when you scatter from an object. And when you do a scattering experiment, usually you make a Fourier transform of the object you're scattering from. So you have a very small nuclei, which is basically a point, and you have a much larger atomic cloud. So when you do nuclear scattering, you scatter from the nuclei. When you do a magnetic scattering, you usually scatter from unpaired electrons which occupy an orbital which has a certain shape in the real space. And if you Fourier transform this, it gives you that these scattering lengths that come from the scattering of the nuclei is basically independent of Q, whereas you have for the magnetic scattering a kind of Lorentzian line shape which decays as function of Q. Okay, so that's for, and now just going to say a bit about neutron scattering, so why it's good. So it's good because, as I said before, the energy and momentum of neutrons are really ideally matched to typical condensed matter excitation. So again, for thermal neutrons, 25 milli-electron volts. Milli-electron volts is the order of magnitude of your phonon energies, of your magnetic energies in many systems. You can go to hot neutrons if it's a bit higher. You can go to cold neutrons if it's smaller, and you can get very high energy resolution. The advantage of having a probe which has almost the energy of what you're looking at is that if I'm looking, for instance, at a phonon which has 10 milli-electron volt, I start with my thermal neutron which has 25 milli-electron volt. One is going to be scattered by the phonons, is going to be left with 15 milli-electron volt. This means I'm changing the energy of my neutron by 50% or something like that. And that's just generally something which is very easy to measure. You know, you start with so it's a relative change which is fairly sizable, so to say. And the big advantage is that all these formula I dropped you here are basically exact. So you can really, in particular for magnetic scattering, it's an exact cross section, and you can really compute that with very little assumption. So that's very useful, but it has intrinsic limitations. Huh? So neutrons are very expensive to produce. So there is a new spallation source coming, which cost, was planned to cost 2 billion euros. So it was 5 years ago. So I guess it's twice more expensive now because it started the construction in 2013 and they will finish it by 2025. And the other way to produce neutrons is to make a reactor. And I'm not sure, you're probably aware that, nuclear reactors are not really fashionable these days. And there are still a couple running in Europe, but they are basically closing one after the other. And 10 years from now, essentially, there will be one research reactor left in Europe. So, so that's, neutrons are good. They're really good things you can do, but to get them is complicated. Overall, you get very low flux, and basically neutron is expensive. When I was studying, I was told that each neutron costs something like 50 cents. So each neutron, so I never checked, but I'm not sure what it includes, but it's, it's probably not far from the truth. So basically every neutron you use, you better make a good use of it. It has a fairly weak cross-section. That's also a big problem. So it requires big samples. And as we'll see after, well, when you're studying new materials, you don't often come with a new big kilogram of single crystals. That's so, and often you have very tiny pieces of crystals, and to grow them in sufficient quantity to be able to do neutrons is not obvious. And finally, the momentum resolution is sometimes a bit complex. So if I go back to my dispersion here, typical momentum resolution looks like this, and this is due to the fact that there is, if you change the energy of the neutron here, you also change sizably its momentum. So you have this kind of ellipsoid. So this can be taken care of very nicely. People doing neutron scattering have a very, very nice way of handling this. But overall, it's not simple. I think as a conclusion, I often ask in my exam to the student, how would they probe, whether a material is magnetic or antiferromagnetic? And they remember the lecture on neutron scattering, and so they always say, "Oh, I would do neutron scattering." I say, well, if you find a piece of material and you want to know whether it's magnetic, this is really not the first thing you're doing, right? It's because it's expensive and it's complicated and it's long. So, but it works. So now, X-rays. So in principle, you can do this as, what you measure with neutrons. You can wonder yourself, well, can I do it with X-rays as well? And now you get into the problem that typical X-ray energies are several kilo electron volts. So that's what I mentioned for wavelengths, which is relevant. So 12 kilo electron volt or something like that. And typical photon energy, for instance, is milli electron volts. So that means that you should be able to discriminate the energy of your scattered photon. So you start with a photon which has 12 kilo electron volt, and you want to see a relative change of its energy of a milli electron volt. And that's much more complicated than starting with your neutron, which has 25 milli electron volt and is losing half of its energy. Now you need a resolving power of 6, 7, 8 orders of magnitude, and that's a different story. So basically, this is coming from Ashcroft-Mermin. So that's that looks fairly hopeless, when you read this in the textbook. It's basically explaining you, well, in principle, it should work with X-rays, but it's not possible. That's for photon. And the second thing is, neutron is a very nice probe of magnetic excitations because they have a magnetic moment, but photons do not have a magnetic moment. So you can also wonder, how am I going to measure magnons with my photons? So that's basically what I plan to tell you after. So first, photons. So do you know what this is? You might have looked at this. So this is basically a reciprocal space that you measure experimentally. So all these big black points are Bragg reflections. But usually when you look at the diffractogram, you get something which is, you have much sharper points. And here what has been done is that it's been overexposed so that you don't see only the Bragg reflections, but you see what's between the Bragg reflection. And you know that if you have a perfect crystal between Bragg reflection, there should be nothing. And what the experiment is telling us is that, well, between Bragg reflections, there are a lot of things. And these lot of things, I'm going to show you in a minute, is coming from photons. So in principle, it's possible, you know, X-rays are sensitive to photons for the good reason that basically when you do an X-ray diffraction experiment, you scatter from electronic cloud. And if this electronic cloud, you know, move and have a dynamics, well, you should be sensitive to that. And you lose basically some intensity in your Bragg reflection, and you have some diffuse scattering between the Bragg reflections. So if you carefully look at this diffuse scattering, it's actually possible to go back and to look at the photon dispersion. So here, it's a very nice example of a piece of silicon, not silicon, and you can see here, so the diffuse scattering pattern in two different planes of the reciprocal space. Two of these pictures are experiment and two of these pictures are simulation. So which one is the experiment? Left, because here you can see there's a beam stop. Okay, good. So, and by analyzing basically this thing, you can reconstruct the full dispersion of the photon spectrum. That's very cool, actually. But it only works here because this is a fairly simple structure. Okay, that's a monoatomic system with a simple diamond structure. So that you can do. As soon as you go for more complicated system, and unfortunately, interesting systems are often more complicated than that, this doesn't work. Though you can learn a lot of things from the diffuse scattering, but you're not able to look at the full dispersion this way, or to extract it that way. So, so in the end, it's only a matter of issues. So to go back to how it works doing the X-ray experiment, I just want to go a last time on the neutrons. This is a triple axis neutron spectrometer. So this was invented a while ago in '57 by Brockhaus, who got the Nobel Prize basically a few months before he died. And basically the principle is always the same. So you start with a beam of particles here, so your thermal neutrons, and you monochromatize them. So it means that you purify their energy. Then they are going to be scattered by your sample, and so you set the momentum transfer by setting the scattering angle here. Okay, and then you analyze the neutrons. You analyze their energy, again, using a Bragg. So you put an analyzing crystals here in certain geometry, and using Bragg law, you can select only some of them with well-defined energies. Okay. If you want to do that with X-rays, it's basically the same principle, but it's a bit more tricky, because you start now with photons that have much higher energy, and that's needed if you want to look at the dispersions. And you want to get an energy resolution which is of the order of milli-electron volts. So you need this kind of beamline. So you need to go to the synchrotron first to get sufficient flux. And the reason why you need a lot of flux is because that photon beam that you get from to start with has to be heavily monochromatized. And this is the kind of excitation that you can look at once you did that job. So you get phonons, you get valence excitation, plasmon, co-excitations, and Compton scattering at very high energy. So how does it work? So here again is the beamline. So you get here a backscattering monochromator, and the sample is here. So the photons are coming from here. They go into this monochromator, and now they are sent back on the sample. They go on the spectrometer and back on the detector, which is next to the sample. I'm just explaining you how it works. So you basically start with an ondulator, which is giving you your X-ray beam. So if you start with something like 10 or 20 kilo electron volt, the bandwidth of that beam is 2 electron volt. Okay, so if you start with an electron distribution of 2 electron volt, there's no chance you can discriminate between milli-electron volt change. So you need to monochromatize this to death. So you have a series of monochromators that reduce that bandwidth, and eventually this backscattering monochromator. So how it works, it's a piece of silicon, simply because you need a very nice crystal, and the nicest possible, crystal you can get is silicon. Okay, and you put this in backscattering, meaning that you get a scattering angle, which I have not written here, of 89.98 degrees. And you look at different Bragg reflection, and depending on the order of the reflection, so you get different energies that match this reflection, and you can monochromatize the beam more if you go to higher order. Essentially, if you take 22 kiloelectron volt here, you get a bandwidth now of 1.5 millielectron volt here, which means that you reduce the bandwidth by 7 orders of magnitude. So this is really high monochromatization. Now, you focus this beam onto a mirror and you send it onto your sample, and it's going to be scattered by the sample. So to find where it's scattered, you put your analyzer somewhere at a given angle, which is going to define the momentum transfer. And what's going to happen is that your analyzer is also a piece of silicon, and you're looking at the same reflection. So now, if you want, if this piece of silicon and this piece of silicon are in the same conditions, essentially, the photons that fulfill the Bragg conditions are the same here and here. The Bragg condition is the same for the two pieces of silicons. And the way you do inelastic scattering is that you change slightly the temperature of the monochromator. By changing the temperature of the monochromator by a few millikelvin, you change the lattice spacing by a tiny bit. And by changing the lattice spacing by the tiny bit, you change a bit the Bragg conditions for that reflections here. And you don't change the energy of the analyzer, so that the photons that are now sent by the monochromator are slightly detuned compared to the photons that need sorry, so the energy of the incident photon is slightly off compared to the energy you need for your Bragg reflection here. And so only the photons that are inelastically scattered, so that have the energy transfer with the interaction of the sample, can now reach the detector. Okay, so and the way you do in practice a measurement, so you look at your reciprocal space. You start with your Brillouin zone center, and you look at the high symmetry points, and usually you align your sample and you set your geometry so that the momentum transfer is going along the path that you want to probe. So for instance, if I want to look at the dispersion along the gamma x direction, I'm going to change the Q angle so that my Q is going from this point to this point. So I'm just going to probe several Qs here and probing the dispersion. I can also do that with constant energies and look at the Q distribution. So that's a bit less usual. And I can do that in different Brillouin zones to look at different type of excitations. Okay, so the important thing here is that basically the momentum that I put in my formula before is the total momentum transfer. Okay, and because my reciprocal space is basically periodic, so you get Bragg vector. So each new Bragg reflection is a new zone center, and the dispersion is probed now as function as a reduced momentum transfer. So I can just have the same reduced momentum transfer in very different Brillouin zone and look this way at different excitations or at different polarizations. So for instance, what I do here, that's here. So if I look here, the mode intensity in my formula is given by Q times the eigenvectors of the phonons to the square. So if I have longitudinal phonons, for instance, with this kind of vibration, so the atoms vibrating along this direction, I need to set my momentum transfer along this direction. Okay, so parallel to the eigen displacement here. Whereas if I want to probe the dispersion of a transverse mode, which will have this kind of vibration for propagation that it goes this way, I can look at it at the same reduced Q, but then I have to change completely the geometry, because what I need to have is a strong projection of my vibration pattern to my momentum transfer. Okay. So we do some kind of simulations before to try to find out, what are the eigenvectors that we expect, because this is governed by symmetry, and we can simulate basically the phone spectrum, and then we measure them, And I can already tell you, so that's the kind of thing that you get. So you measure different energy scans as function of 4 different momentum, and you get basically the dispersion, and you can plot the dispersion. So very often it's boring, put it this way, and it's getting very interesting when you don't get what you calculate. And there are a couple of systems which is the case, and I'm going to illustrate that in a minute. But before that, my last set of formulas almost, how it works for X-ray scattering. So I need still to calculate my matrix element here, and the interaction of X-ray with electrons is basically of that form. So it's basically involved, so it's basically electron in an electromagnetic field, and so you need to put here the vector potential. Yeah? So that's the good old vector potential from electromagnetism. And it's not a very convenient way of treating the problems, and a more convenient way is to quantize the field and to use the so-called second quantization. So I don't know whether you did this in advanced quantum mechanics maybe or something like that. So basically there is this form for the potential vector here, which is basically describing the electromagnetic field in terms of photon creation and annihilation operators. Okay, so each photon has a polarization, a momentum, and an energy. Okay, and you describe the whole potential vector using this photon creation and annihilation operators. And then you need to remember what you want to do when you do a scattering experiment. When you do a scattering experiment, you start with a photon here,